This video, we'll be learning about Huffman encoding. Hi, I'm Perel, a first-year electrical engineer, and I actually learned about Huffman because of a bet my dad made with me about a year ago. So Huffman encoding is a lossless data compression method. Essentially, it compresses the space, for example, an email takes without losing any of the data inside of the email. Our computers speak in binary, which just means that instead of our alphabet, they use ones and zeros. Now I'm going to quickly go over memory. There's a certain amount of space for photos and apps on our phones and computers. Memory is that space allocated for those photos and apps. And just like distance, which can have a unit of meters, memory has a unit of bits. Usually, our data is stored in 8 bits each, for example, a letter B when using ASCII encoding. What happens when you have too much data and too little memory? We compress it, in this case using Huffman encoding. Huffman has 3 parts to it. 1. Find the probability of each letter and character. 2. Creating the binary tree that gives us a path to follow for each character. And 3. Using the binary tree to encode the message. Let's say that we're trying to send Mississippi. To find the probabilities of each character, we simply count how many of each there are and divide that by the total length. To create the binary tree, we'll first write the characters from greatest to least probability. Notice that S and I have the same probabilities, so those two are interchangeable. Then we're going to build a tree from bottom up. Add the 2 probabilities that will create the least total probability. For this first one, that'll be P and M, adding to 3 over 11. This creates a new node called PM. Then repeat that grouping. S and I would make 8 over 11, while I and PM would make 7 over 11. We group I with PM and form a new node, IPM. We're left with S, so we just add that again. Make note that the total probability is now 1, and the top node contains all of the characters that were in the bottom row. I'm going to remake that tree just so it's clear to see the binary. For branch on the left, write a 0 next to it. For branch on the right, write a 1 next to it. To find S, we just follow the tree branches down until we reach an endpoint, which is just the first left branch. Then, for I, it's right, left, 1, 0. P is right, right, left, 1, 1, 0. And M is right, 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 1, 1, 1. To decode, it's the same thing. If the first binary is a 1, we go to the next right node and read the next binary. If it's a 0, we go to the next left node. And if there's nowhere else to go, we know that 1, 0 is an I. To encode without Huffman, we'll use ASCII encoding, which is 8 bits per character. So multiply 8 by the 11 characters, and you get 88 bits, while Huffman is only 21 bits. You'll definitely see the difference between Huffman and ASCII from the result. Huffman is used daily, compressing huge files. One example is a 16 by 8 pixel image with 8 bits per red, green, blue channel. It has 3072 bits without compression, but with Huffman, it's 2432, which is a 30% decrease in memory. Imagine the space a larger, more complicated image without Huffman takes. Huffman compresses that amazing photo you took on that hike into a JPEG. Whether you recognize it or not, Huffman is the basis, if not core, of every compression scheme used for your music, pictures, and video games. Thanks for listening. I really hope this helps.